Assalamualaikum warahmatullahi wabarakatuh. Good afternoon. Um, Today, this is the last week or last material about the inverse Laplace. I will show you how to solve the circuit directly using the Laplace transform. And yeah, actually, as you know, that Laplace method is very useful if we can use this transformation to solve the differential equations. And if you remember that if we have a, a circuit, the passive component is like capacitor and inductor in the circuit, and we make circuit analysis, we got that this equation will be towards to the differential equations. So it's a little bit difficult to solve the, the equations, the circuit equation using the differential equation method. It's like ordinary differential equation that we already discussed in before the quiz one. So here, actually, I already explained this method how to solve the circuit analysis using the Laplace. Okay, so the first one we have to analyze. The step is we have to analyze the circuit using the time domain, using the familiar analysis. We can use the Kirchhoff. We can base on the circuit nodal, or we can based on the current or based on the voltage. And then after we got the equation in the time domain, we have to perform Laplace transform. I mean that we have to transfer from the time domain, the equation in time domain, to the S domain, and then we solve the frequency domain algebra expression in the S domain, and then we transform back to the time domain. Okay, so I want you. So you have to remember, if we have the three passive components like a resistor, inductor, and then capacitor here. This is the first one is the resistor. So the voltage of resistor or VR is R dot IR, or the resistance dot the resistor current. And then so this is in time domain, and if we transform to the S domain, it's a little bit the same, but just the differences is just the notation from the time domain to the S domain, like this one. So another is similar, and then we can get the constant or R here by using the VR per IR. Okay, and then this is the notation in the S domain. And then if we have another passive component like the capacitor here, so the capacitor current is in the time domain is C dVct per dt, the differential of the capacitor voltage per time. So if we transform the differential to the S domain, so we got that IC in S domain is C S C C S. Okay, so this is the Laplace transform of the differential. The C is the constant here, and then dVc per dt become SCC S. And then if we want to calculate the impedance, the capacitor impedance, so we divide the Vc per Ic. It's like in resistor, we divide Vr per Ir to get the impedance, the resistor. And then so this is the impedance of the capacitor. So Vc per Ic is 1 per Sc. Okay, so this is the notation in the S domain, and similar if we have the inductor here, this is the current flow in inductor, and then this is the VL, the inductor voltage. So in the physics, VL in time domain is L dIL per dt. So if we transform to the S domain from the time domain, the VL is similar, and this is the constant or similar, and then this is the differential. So we got that this will be SIL, similar to the capacitor as VCS. So if we want to calculate the impedance, the inductor impedance, so VL per IL is SL. So this is the notation. Okay, so the impedance of the resistor is similar. ZR is R, and then impedance of the capacitor is 1 per SC, and then impedance of the inductor is SL. Okay, so from here we notice that the C from the capacitor, the capacitive impedance, and then ZL for inductive impedance, it depends on the frequency. Okay, so but for the given frequency they are constants. Okay, and then we have to transform also another characteristic in circuits like the voltage, the currents, of course using the S domain. Okay. So this is the summary. So we have to transform the circuit to the S domain, and then we solve the circuit and transfer back to the time domain. Okay, so the first one, find the Laplace frequency domain in the RC circuit like this one. If we have the input step or step function here, so this is the input step, Vi is the input step. So Vi is Vf dot ut. This is like a battery. So like the battery or DC voltage, T equal to 0 is on, T lower than 0 is off. Okay, so we have to the first one, we have to convert this circuit to the S domain. So VIT becomes VIS, and then R becomes ZR equal to R, and then C, this one, C becomes ZZ, the impedance of the capacitor, and we have the voltage of the capacitor. And then we notice that the C is 1 per SC, like my explanation before. This is the capacitive impedance. And then because of this is the UT or step function, so VI is VF per S. Because the step function, the UT is 1 per S. The Laplace transform of UT is 1 per S. So this one is VF per S. Okay, so the frequency domain of circuit we can easily solve by using the voltage divider. Vc here, Vc, the capacitor voltage is Zc per Zc plus Zr dot Vi. And then we put the Zc is 1 per Sc and Zr is R. So we got this one, multiplied by Vi. And then we replace Vi by using Vfs. So we got these equations. Okay, so Vc S become Vf per Rc per S multiplied by S plus 1 per Rc. Okay, and then this is the example 2. We use the same RC circuit, but we use the sinusoidal source like this one. Vi is equal to Va cosinus omega t. Okay, so similar, we convert the circuit to the frequency domain. So, and then the difference is only the input voltage here. Because of the Va cosinus omega t, the cosinus omega t transformed to the Laplace transform is S per S quadrat plus omega quadrat. Va is constant, so we just multiply to Va. And then similar to a previous example, we use the Vc is voltage divider. So we got a similar result here, but Vi is different. Va S per S quadrat plus omega quadrat. So we got that VCS is this one. Okay, so this is how we solve this one. And then this is the example 3. Find this one unit step, but we put another passive component, it's like inductor here, L. So similar method, we convert to the S domain. Vi is unit step become Vf per S, and Zr is R, Zc is 1 per Sc, and Zl, inductor impedance, is Sl. And then using the voltage divider, how to find Vc. Vc becomes Zc per Zr per Zc per Zl dot Vis. So we use the S domain for the ZC, ZR, ZC, and ZL here. So we got this equation and we convert VI to the VF per S. So we got this equation to represent the capacitor voltage. And then the example 4, using the sinusoidal source VA cosinus omega t is similar method how to solve the example number 3 here, but we only change the V input using this one. Okay, and this one, if you want to use the operational op-amp here, I think op-amp I skip for the op-amp because you have to learn the characteristic of op-amp first before I give the example. For the example only from the example number 4 is this from the simple circuit. Okay, I think this is enough for the brief explanation about the how to solve the circuit using the Laplace transform. Thank you very much. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.